Okay, so far we have discussed about the first law of thermodynamics. The mathematical form of the first law of thermodynamics is given by the heat given to a system is utilized for increasing the internal energy as well as doing the external work. Also, we have discussed different type of thermodynamic processes. For an isothermal process, we can write PV is equal to a constant. For a adiabatic process, we can write PV raised to gamma is equal to a constant is some other constant. So now if we consider an isothermal process and adiabatic process, when a system undergoes in two situations these two processes, then from the state A to B, the isothermal process can be represented by a curve like this. So the equation of this curve is PV is equal to a constant. Now if you consider the slope of this curve, which is equal to dP by dV, from this equation PV is equal to K, we can obtain the expression for dP by dV as if you differentiate this equation, PV is equal to K, if you differentiate it, P into dV plus V into dP is equal to 0. So rearranging this one, dP by dV will be equal to minus P by V. Now if you consider the adiabatic process of the same system, the system changes from one state to another through an adiabatic process. Then the equation of state of this curve is represented by PV raised to gamma is equal to some constant. Then differentiating this equation, we will get the slope of this adiabatic curve. So here it is the slope of isothermal. Then differentiating this one, V raised to gamma into dP plus gamma into V raised to gamma minus 1 dV into P, so P into dV is equal to 0. So if we take this PV raised to gamma outside, so here the first term will be dP by dV, P plus gamma times 1 by V dV is equal to 0. Here PV raised to gamma cannot be 0, it is a constant, so what remains is dP by P plus gamma times 1 by V dV is equal to 0. dP by P plus gamma into 1 by V dV equal to 0 can be written as dP by dV is equal to gamma times 1 by V dV. From this one we will get dP by dV as minus gamma P by V. So this dP by dV is the slope of adiabatic process. So from these two equations we can say that dP by dV for isothermal process is equal to minus P by V and dP by dV for adiabatic process is minus gamma times P by V, which is the slope of isothermal, and here it is the slope of adiabatic. So we can say that slope of adiabatic curve is equal to gamma times slope of isothermal. So if we draw these two processes, adiabatic and isothermal, on the same PV diagram, then if it is an isothermal process, then adiabatic process will have much bigger slope. So we can say that adiabatic means it is the curve representing the adiabatic process. Adiabatic is steeper than isothermal, or the slope of the adiabatic process is gamma times the slope of the isothermal process. So that is the relation between the slope of adiabatic and isothermal process. Now let's see another application of first law of thermodynamics, that is the relation between Cp and Cv. You are familiar with the relation Cp minus Cv is equal to capital R or small r if the substance is 1 mole, N is equal to 1 mole, then this equation will be Cp minus Cv is equal to capital R. The relation between the specific heat at constant pressure and specific heat at constant volume. To get it, let's consider the internal energy, and you know that the internal energy of a system is a single valued function of the thermodynamic variables pressure, volume and temperature. It is always better to take any two of them are independent, because for an isothermal process we know that PV is a constant, for an adiabatic we know that PV raised to gamma is constant. Any two of the thermodynamic variables are sufficient. So I am considering the internal energy here as a function of temperature and volume. Then I can write the differential of u, that is du, as from mathematics I can write it as dou u by dou t at constant volume into dt plus dou u by dou v at constant temperature into dv. Let it be equation number 1. According to first law of thermodynamics, we know that del q is equal to du plus P dV, that is heat given to a system is utilized for increasing the internal energy as well as doing the external work. So substituting du from the equation number 1 here, we will get dou u by dou t at constant volume into dt plus dou u by dou v at constant temperature into dV plus P dV. But we know that dou u by dou t at constant volume is nothing but Cv into dt plus dou u by dou v at constant temperature plus P into dV. Here dV is a common factor. This equation dou u by dou t Cv is obtained from here, that is Cv, the definition of Cv is del q by dt, rate of change of heat with respect to temperature at constant volume. Then this is given by, according to first law of thermodynamics, del q is equal to du plus P dV divided by del T. So del Q at that is du plus P dV at constant volume. At constant volume dV goes to 0. So what remains is du by dt, that is dou u by dot t at constant volume. So that's I am using here as Cv. Now we need Cp also, but we know the expression for Cp, that is specific heat at constant pressure is the rate of change of heat with respect to temperature del Q by dt at constant pressure. So I am dividing this equation by dt, then this is equal to Cv into dt by dt by dt at plus dou u by dou v at constant temperature plus P into dV by dt. Now make this expression in terms of constant pressure. So del Q by, in order to change into Cp, so this del Q by dt at constant pressure, which is equal to Cv into dt by dt at constant pressure is 1. So Cv plus dou u by dou v at constant temperature plus P into dV by dt at constant pressure. So this is equal to del Q by dt at constant pressure is Cp is equal to Cv plus dou u by dot t at constant temperature, dou u by dou v at constant temperature plus P into dV by dt at constant pressure. Now you know that if you consider this one dou u by dou v, it is the change in internal energy with at constant temperature. When temperature is constant, the internal energy is always constant. So change in internal energy at constant temperature is 0 always. And also we know that PV is equal to RT for an ideal gas or perfect gas. Then PdV, differentiating this one, we get PdV plus VdP is equal to R dt. So this can be written in this way: P into dV by dt at plus V into dP by dt is equal to R. Now if we make pressure constant, then this equation becomes P into dV by dt at constant pressure plus V into dP by dt at constant pressure is 0 is equal to R. So if we make these two substitutions, dou u by dou v at constant t is equal to 0 and P into dV by dt at constant pressure is equal to small r, then this equation becomes, let it be equation number 2, that becomes Cp is equal to Cv plus 0 plus P into dV by dt at constant pressure. So P into dV by dt at constant pressure is small r, so Cp is equal to Cv plus small r, or Cp minus Cv is equal to R. which is equal to N into R. So for 1 mole of a substance, N is equal to 1, then Cp minus Cv is equal to capital R. So this is the relation between the specific heat capacities at constant pressure and volume for an ideal gas. It is obtained by applying the first law of thermodynamics. Now if we consider the latent heat, latent heat is the quantity of heat absorbed per unit mass. Quantity of heat absorbed per unit mass of a substance during the change of phase, that is from solid to liquid or from liquid to vapor without changing temperature. So you know that for example, if you consider the water at 100 degrees Celsius, water will be in the liquid state as well as in the gaseous state. So when a liquid water at 100 degrees Celsius absorbs a certain quantity of heat Q and it becomes water in the gaseous state at 100 degrees Celsius, then this quantity of heat is referred to as the latent heat. It is actually called the latent heat of vaporization. So if it is from liquid to gas, it is called latent heat of vaporization. If it is from solid to liquid, it is called the latent heat of fusion. If it is from so this latent heat of vaporization, latent heat of fusion, etc. So latent heat means it is the quantity of heat absorbed by a substance per unit mass during the phase change without rise in temperature. The specific heat is actually the quantity of heat absorbed by a unit mass substance to rise its temperature 1 degree Celsius. So here this heat of vaporization is actually the sum of two distinct quantities of heat. They are the heat required to perform the internal work in pulling the molecules apart from each other. That you know that when liquid goes to gaseous phase, the intermolecular separation will increase. So some quantity of energy is needed for pulling the molecules apart. So the latent heat, the quantity of heat supplied to a system, will utilize to increase the intermolecular separation when it changes from one phase to the another. And also the another part of energy is utilized for doing the external work. So we can say that the heat of vaporization, if you consider specifically the heat of vaporization, it is latent heat of vaporization. It is the sum of two distinct quantities of heat. One is the heat required to perform internal work in pulling the molecules apart. So when molecules are pulled apart, the internal potential energy will change. So this part is actually the change in internal energy, UF minus UI. Now the other part is the heat required for to perform external work in expanding against the in expansion against the external pressure. So this is actually the part of the external work done by it, that is PdV or P into Vf minus Vi. So the latent heat can be expressed as quantity of heat absorbed per unit mass of the substance in changing the phase without rising its temperature, that is, it is equal to increase in the sum of the increase in the internal potential energy UF minus UI plus doing the external work, that is P into Vf minus Vi. So this is the expression for the latent heat. So that's all about the first law of thermodynamics. Now two more quantities we have to calculate just by knowing the equation of state for isothermal process and adiabatic process, which is the isothermal and adiabatic elasticity of the gas, that we will discuss in the next video. Thank you.